Hey, it's Mrs. Cat, and I'm here to look at worksheet 3 in Unit 4, which is going to give us an introduction to definite and multiple proportions. So we are going to be given some mass data for some different elements in a pair of compounds, and then asked to do a few different things with those masses to make some comparisons. Right now we're going to look at compounds of carbon and oxygen. So we've got compound A with 57.1 grams of oxygen and 42.9 grams of carbon. Compound B has 72.7 grams of oxygen and 27.3 grams of carbon. First thing that we're going to do is find the value of the ratio between the mass of oxygen to the mass of carbon for both of those compounds. Now, I'm going to show my work up here right next to those masses that we were given to begin with. So I'm going to go compound A, and that's going to be 57.1 grams of oxygen to 42.9 grams of carbon. And I want to go ahead and just divide that. Okay, so we're going to get a nice decimal number. Okay, and we get about 1.33. So I'm going to make this a ratio of 1.33 grams of oxygen for every 1 gram of carbon. Okay, that's compound A. And do the same thing for compound B. Just a little quicker this time. 72.7 grams of O, or 27.3 grams of C. And this time I get 2.66. Okay. So same thing, I'm going to make that 2.66 grams of O for every 1 gram of carbon. Okay, so that's going to take care of part A. Okay. Part B, how do these two mass ratios compare to one another? So I'm going to go ahead and highlight these two mass ratios for A and B, 1.33 to 1 and 2.66 to 1. So we can see that B is twice as large as A. It's double. Okay. Let's take these and express these ratios as improper fractions. So 1.33 is 1 1/3. To make that into an improper fraction, we're going to make that 4/3. So that means I want to put my units on here as well, right? So it's not just 4/3, it's 4 grams of oxygen over 3 grams of carbon, right? Double that for B. We want to keep it with a common denominator. So we're going to keep that 3 grams of carbon on the bottom. That way we can compare these two pretty easily. So I'm going to make this 8 grams of oxygen on top. Okay, now that we've done this, we're going to use this information to sketch some particle diagrams using 2 hypotheses. Okay, first hypothesis is hypothesis 1, and we're going to make the assumption that atoms of carbon and oxygen are going to have the exact same mass. Okay, so let's just go ahead and do that from the start. Okay, I'm going to use little particle diagram pictures, and I'm just going to use a circle to show carbon and oxygen as being the same, hopefully, if my pencil is going to cooperate here. So let me reconnect here. I'm going to make them the same size. I'm going to use my elemental symbol and a little numerical symbol in there to show that they are going to be the same. So I'm going to have oxygen as 1 as well. Okay. In order to do this and to keep these ratios, either the 1.33 to 1 or the 4 to 3, we need to make these whole particles. So that means in order to show this with this hypothesis, we're going to want to use those improper fractions. So in my particle diagram, this means I want to use 4 oxygens and 3 carbons. So I'm going to start with my 3 carbons. I'm just going to put them all together. I'm going to use the same color because I'm going to put that symbol in there to show that they're the same. Now pretend like they're all the same size. Right? So every 3 carbons is going to give me 4 oxygens. And we're again saying that these all have the same mass. Right? Oxygen 1, oxygen 1. Okay? If we can figure out the formula for that compound, we can see exactly what it is, right? We have a total of 3 carbons, so we're going to make it C3. We've got a total of 4 oxygens, O4, right? Same idea for compound B, but we know we have twice as much oxygen. So I'm going to start with the same 3 carbons. Again, I'm going to try my best to make all of my particles the same size. That never really works out for me very well. And then I'm going to add in 3, 4, 5, 6, 7, 8. Those are all going to be oxygens. And they're all going to have that mass. We're just going to say it's a mass of 1. Doesn't really matter what it is. We do just want to make sure that it's the same. I'm going to use the mass of 1 just to keep it simple and easy. Okay? So again, same thing to get that formula. We've got 3 carbons and 8 oxygens. Okay, so there's going to be our 2 formulas, C3O4 and C3O8. Okay. Now, hypothesis number 2, we're going to say that the atoms of oxygen are heavier than atoms of carbon by the ratio that we have in compound A. So remember that ratio was 1.33 grams of oxygen for every 1 gram of carbon. Okay, that was compound A. So when we draw our particles this time, those are the mass values that we want to use relative to each other. So we're going to still say that carbon has a mass of 1, but we're going to say that oxygen is 1.33 times bigger. So I'm going to try to show that oxygen particle to be a little bit bigger, but I'm also going to put that mass number in there. Okay. The only way to account for this ratio that we have of 1.33 to 1 or 4 to 3 is to use these 2 particles together. Okay, if I use 1 carbon and 1 oxygen, that'll take care of that ratio, 1 and 1.33. Okay, so I only need 1 of each. Carbon is 1, and again, I'm going to try to show that that oxygen is going to be a little bit bigger. Okay, 1.33. Now, remember that compound B, our ratio is 2.66 to 1 for oxygen to carbon. So I want to keep the amount of carbon the same. So I still want to use 1 carbon with that mass value relative of being 1. But this time I have twice as much oxygen, so I want to use 2 particles instead of 1. Okay, so oxygen is 1.33. Oops, oxygen is 1.33. Okay. Again, this time we still want to use the number of atoms that we have of each element to come up with our formula. This time, oops, I forgot my other 3. Compound A is going to be 1 carbon and 1 oxygen, where compound B is going to be 1 carbon and 2 oxygens. Okay. So those are possible formulas. We don't really know which one's right yet. Okay, same idea, looking at a different set of compounds. This time we're going to look at copper and oxygen together. Okay, keep in mind we're going to go ratio of copper to oxygen. So we're going to kind of do the same thing here. I'm going to divide those 2 values. I'm going to show my work with this, okay, and see what we get here. So, whoa, compound A, don't want my highlighter. Compound A, I'm going to go 79.9 grams of copper for 20.1 grams of oxygen. Do my math real quick. Whoops, helps if I type in all my numbers. 79.9 divided by 20.1 gives me 3.975. We're going to call that really, really close to 4. So we're going to say about 4 grams of copper for every 1 gram of oxygen. Okay, compound B, these are masses that were given, 88.8 grams of copper for 11.2 grams of oxygen. Actually, we'll call this here again. This one's going to be about 8. Okay, let me do my math to give you an actual value. 88.8 divided by 11.2 gives me 7.9285. We're going to call that really, really close to 8. So we're going to say 8 grams of copper for every 1 gram of oxygen. Okay, again, I want to highlight those just because we're going to need those. Okay, same thing. That takes care of part A. Part B, we see again that these compare, that B is double A. Now, it doesn't always work out this way, but that's what we have in these examples. Okay, we don't have to do anything different for these to be improper fractions. Okay, but let's go ahead and write them anyways, just so we have them closer. 4 grams of copper for 1 gram of oxygen for A, 8 grams of copper for 1 gram of oxygen for B. Okay, same thing, right? Let's keep those ratios on the screen. Same thing here. We're going to use these same two hypotheses, okay, that they have the same mass for copper and oxygen for hypothesis 1 versus different masses based on the ratios for part 2. Okay, so we're going to have about the same size particles for copper and oxygen. Okay, we're going to make these look a little bit different though. Okay, I'm going to start with my 1 oxygen, and then I'm going to put 4 coppers on there. These are not great in terms of being consistently shaped particles, but you get the point, right? So we're going to call this Cu4O for our formula. Okay. Now the second one here, we've got 8 coppers for every 1 oxygen. That's going to look a little crazy, but I'm going to try my best to get it all in here. My connection keeps freaking out a little bit, so give me just a second here. We've got 1 oxygen and 8 copper. So I'm going to do my best to get these all in here. 1, 2, whoa, that's not connected. 3, 4, 5, 6, 7. That one's funky. Let's go. 7, 8. Good enough. Everything's attached somehow. We can tell it's a compound. So I'm going to show that these are all coppers and they all have a mass of 1. Again, these are just relative masses to show that they're either the same or different. Okay, so let's go copper, copper. Another way I could do this would be to show different colors and show these symbols and masses in here, but I'm just going to keep it consistent with what we were doing before. Cu8O for our formula. Okay. If they're heavier by that ratio, the copper is heavier than oxygen by the ratio of the compound A formulas, then we've got 4 to 1, right? And so when we draw this, I'm going to try my best. Woo, maybe not in highlighter. Let's call that copper. Let's call this other one oxygen. I'm going to try my best to make copper about 4 times bigger, because not only do I want to show that with the mass value that I'm going to put in my particle, but I like to show it visually too. So here's our oxygen out of ratio of 1. So 1 copper, 1 oxygen for that formula. Okay. Now, if I've got double the ratio for compound B of copper mass to oxygen mass, I want double the number of particles. So we're going to wind up with an oxygen and 2 coppers. Again, we're going to pretend like those are the same size. And then we're going to make that Cu2O. Okay, so the big question here is, which one of these seems more reasonable? Hypothesis number 1 or hypothesis number 2? Or hypothesis 1 is all of those atoms are going to have the same mass, versus hypothesis 2, where the masses of the atoms are going to be different and they're going to be based on those ratios. Well, if we take a look at both of our examples from number 1 and number 2, both the copper and oxygen compounds and the carbon and oxygen compounds, To me, I see that one makes more sense than the other. And that just is out of simplicity's sake. To me, the simple ratios we get with hypothesis 2 of 1 and 1 or 1 and 2, like we had in our carbon-oxygen compounds, okay, versus 1 and 1 and 2 and 1 that we have in hypothesis 2 for our second compound, those seem to make more sense to me than 1 oxygen and 4 coppers, or 1 oxygen and 8 coppers especially. That one seems a little crazy and hectic, okay? Versus our carbon ones, 3 and 4 for carbon oxygen, 3 and 8. Those just seem a little wacky. And that's for good reason. That's because hypothesis 1 is not actually what winds up happening. So what we're going to say with these is that, you know, it makes more sense that hypothesis 2 is more reasonable. Whoa. Okay. And we could say for a couple of different reasons. Now, your reasoning might be a little bit different than mine, and that's fine. Okay, but what we really want to know is that we're going to use the second hypothesis, that these atoms have different masses. When they combine into compounds, they're going to be based on those ratios between those masses. And we could give a couple different reasons here. I already gave one that it gives us simpler, more realistic seeming compounds, like, you know, carbon dioxide, CO2, carbon monoxide, CO. Those compounds are ones that you know from experience and maybe from other courses. So we get simpler compounds. From mass ratios. In the past, I've also had students just say, well, I already know that different elements have different masses, so it can't be the first hypothesis that says that their masses are the same, which is great, because I hope by this point, okay, that you already know that different elements have different masses. Now, we'll talk soon about why they have different masses, okay, but we're definitely going to be using hypothesis 2 to make these compounds. We can also see from this that we can use the same combination of elements to make different compounds based on the ratios of masses that we have, and that's what you're going to show me again in the remaining problems on worksheet 3. So you've got 2 more that you're going to work through on your own. First one is going to be 2 compounds of copper and chlorine. This is still broken down in those same steps. Find your ratio, compare them, and then you'll find that simplest formula for compounds A and compounds B. This isn't going to ask you to draw the particle diagrams, but that may be something that would be helpful to you when you're working through this. Okay. Number 4 is going to take you through a couple more steps. This one is not going to be quite as clean and simple as the other, but make sure that you read particularly part B to help you with those ratios in between, and you'll find out those formulas with no problem. So you're going to go ahead and complete these, number 3 and number 4 on worksheet 3, and then you'll submit them when you're done and check your answers. Let me or your own individual chemistry teacher know if you have any questions. Thanks. I'll see you again soon.